Presentation in Unit 7. It's called It's Just a Phase. This is sometimes you have to go through a phase whether you like it or not. So the learning goals for this particular presentation are number one, that you describe the energy of phase transitions. So you're familiar with melting and vaporizing and evaporating and all those sorts of things. We're going to describe the energy as it relates to those. That you be able to describe the three methods of heat transfer, and that you be able to calculate the energy required to change phase. So what we already know that when you add heat to a system, it can increase the temperature of a system. That's what 7.1 was really all about, was using this Q equals Cm delta T or Q equals MC delta T. It's the same thing. We've put energy into a system, it changes the temperature, but we do know that it can also change the phase of a substance, and that's actually what we're focused on for this presentation. In the lab, you should have learned that when energy comes into direct contact with something, it can be transferred by direct contact. So it can go to the atmosphere. If you touch something, it can be hot or it can burn you. But you should know that energy can also be transferred by sunlight. You should have seen a distinct temperature difference whenever you use foil versus saran wrap as far as these temperatures are concerned. There should have been a change in temperature between the two. We also learned that the larger the exposed area to the sunlight, if you had something larger like this, it would have a greater change in temperature than this one because it's exposed to more sunlight. Okay, so let's look at phase changes. So the first thing we know is we generated a graph that looks like this in the 7.1 lab. And we talked about this right here. How can you have this plateau here when you're inputting energy into a system? That energy has to go somewhere. And what a phase transition actually is the energy is going into what we call potential energy. But really that potential energy is this. It's breaking the bonds, or not the bonds, it's breaking what we call the intermolecular attractions. Okay, every oxygen, every hydrogen has what we call a partial positive and a partial negative. Those partial charges right there are attracted to one another. So when you're putting energy into the system and it's not changing the temperature, what it's doing is it's breaking this attraction. It's pulling them away from each other. Think of them as magnets, and they're attracted to one another, and you have to put energy in to pull them apart. And that's basically what we're doing when we put in energy into a system and the temperature doesn't change. So the first transition we have is from a solid to a liquid, or a liquid to a solid. Generally this whole thing is called fusion, but sometimes we want to be a little bit more specific. So we say fusion is the process in which you go from a liquid to solid, and that's fusion's the right term, but freezing is more common. Okay, it requires the loss of heat, so that means it's an exothermic transition. And because of that, you're losing heat, and as it loses heat, you have a minus Q value. Now, whenever it melts, you're having an energy input, and that energy input makes it an endothermic reaction and means you have a positive Q value. So the energy required to fuse, so the energy required to take a solid and go to a liquid, say it takes 100 joules to do that. Well, if I take this liquid and I remove 100 joules, I would go back the other direction. They're equal values, and the reason for that, once again, is conservation of energy. Conservation of energy. Okay, so now the next phase transition you're probably familiar with as well. It's going from a gas to a liquid, or a liquid to a solid. We call the first one condensation. It says it requires a loss of heat because you're actually giving heat away and cooling from a gas to a liquid, so it's a minus Q value. We have vaporization, which requires a heat input, so we call that an endothermic transition from a liquid to a gas, and has a positive Q. Once again, the energy required to go from one to the other are just opposites of one another. So for example, if it takes 100 joules to go from a liquid to a gas, then if I take 100 joules away, then I'll go back from a gas to a liquid. Conservation of energy. The last one you may not be as familiar with. It's called a gas to solid, or a solid to gas. It's called crystal lattice formation whenever you're transitioning from a gas to a solid, but once again it's the same idea where you're putting in, this should be exothermic transition, as you're taking, it requires the loss of heat. So this right here is an exothermic transition. And then sublimation requires energy input. It's an endothermic transition. So once again, you're putting heat in and going from a solid to a gas. This is an example right here. You see dry ice. Now dry ice doesn't have a liquid state. Instead, it goes straight from the solid to the gas phase. So the heat required to sublimate is the same. So once again, law of conservation of energy. 100 joules this way, 100 joules that way. So they're the same values. Okay, next we have the change of phase equation. We have Q equals ml. Q we're familiar with as heat. M we're still familiar with as mass. But now we have this L term. That's the only new term, and that's what we call the latent heat of transition. What that is every substance has a set value for how much energy is required to change phase. So this is a constant. It's something that you would look up on a table for each particular substance and each phase change. So the energy required to vaporize does not have to equal the energy required to fuse. Those are two different things. Now, if you were talking about the heat required to fuse or freeze, you would say that is the same thing as the L required to melt. Okay, because those are basically the same phase transition. So you have to be real careful with your L value as far as what you're looking at. The first one says, why is less energy required to change from ice to water than water to steam? So if you look, the amount of energy that's required to go from ice to water is relatively small. It's on the order of like 334 joules per gram. So that's pretty small. Where on the other hand, with steam, it's like 22,600. Now if you think about the phases themselves, remember that if you look at it on an atomic basis, the molecules are stuck together in a solid. And in a liquid, they're not stuck together. They can kind of rotate from one another, but they're still really close to each other, and they still have this attraction to one another, that intermolecular attraction. Well, when you go from a liquid, where they're kind of rotating relative to one another, to they are very far apart and have nothing to do with one another, okay, that's the difference right there. You have a great deal more energy going into breaking this attraction right here. So there is no attraction between these gas molecules. There's a big attraction here and a kind of big attraction here. Here it's kind of big and here there's none. So there's a big difference in the amount of energy that's required to change phase. In addition to that, you can think of it this way. Both solids and liquids are confined by gravity, whereas gases are not. So think about it, if you're giving it enough energy to go against gravity. Okay, the next one says, how much energy is required to convert 5 kilograms of 100 degrees Celsius water into 100 degree steam if the latent heat of vaporization for water is 2,260,000 joules per kilogram? So what I want to know is energy. Specifically, I'm looking at heat. I want to know the energy required to convert 5 kilograms from 100 C water to 100 C steam. Okay, so because of that, it's the same temperature. There's no change in temperature. I'm just changing the phase. I'm changing from water to steam. So because of that, I can use the formula Q equals ml. That's the only one that I can use if I'm changing phase. If I'm changing temperature, it's something different. So as a result, I can say m is 5 kilograms. I can say the latent heat of transition is 2,260,000. Got too many commas in there. Okay, and I can multiply it out. Q equals 5 times 2260000. Okay, and whenever you take those things and multiply them out in your calculator, you should get something on the order of 11,300,000 joules. So one of the things that I do want you to be aware of is look how much energy is required to change the phase. 5 kilograms of water is not a lot. That's a large bowl, or it's not even a large bowl, it's a bowl of water that you would use. It's about 11 pounds, it's a little bit more than a gallon, about a gallon and a half. It takes 11,300,000 joules for you to vaporize that once it's at 100 degrees. So after it's already, you raise the temperature to 100 degrees, it takes 11 million more to get rid of all of it and convert it into steam. It's a lot of energy. The mastery level question says how much energy is required to heat 10 kilograms of 0 degree ice to 50 C water. Okay, so this right here is a little bit different because I'm changing both the phase and I'm changing the temperature. You can't change both at the same time. So instead we have to take this as a stepwise approach. Okay, so the first thing I want to do is I want to look at, I'm at 0 C ice. So if I'm at 0 C ice, okay, the first thing that I can do is I can change phase. Because at 0 degrees Celsius, that's where it actually converts, and it can go from 0 degrees Celsius water. Then in a second step, I can go from 0 degrees Celsius water to 50 degrees Celsius water. So basically I have two steps here. The first step is a phase transition, so it's ml. The second phase is a temperature change, so it's Cm delta T. So if I can calculate the energy required to change phase and the energy required to change temperature and add them together, that's the total amount of energy that's required. So I want to look at it, I want to say, okay, I'm going to say this one is QP, because that's a change in phase, and I'm going to say QT. Well, QT is not great, and then I'm going to have Q total. Okay, Q total is going to be the sum of the two, the Q required to change phase and the Q required to change temperature. So now if I look at my given information, the first thing that I'm given a mass of 10 kilograms. I'm given a change in temperature of 50 degrees Celsius, and I'm given the latent heat of transition and the specific heat of water. Okay, I'm going to go ahead and just point to those so I don't have to rewrite them. So now, if I know that the total energy required is QP plus QT, I can write it as Q total is equal to ML plus CM delta T. Or, if we put in our numbers, 10 times 334,000 plus 4184 times 10, I'll run out of room, times 50. Whenever you multiply those out, 10 times 334,000 plus 4184 times 10 times 50, you end up with something about 5,432,000 joules. Now, just to put it in perspective, this right here is 5 million joules. This was 11 million joules. So it takes over twice the amount of energy just to change from a liquid to a gas as it does to go from a solid to a liquid and raise the temperature 50 degrees. Okay, you can raise it from 0 degrees Celsius ice all the way to 100 degree water, and it would still take less energy than it would to just change the phase from water to steam. That's a big jump right there. Okay, next, thermal equilibrium, just as a review, says objects move towards thermal equilibrium, so the heat must be transferred to reach thermal equilibrium. So somehow it's got to go from here to here. Now there are three methods of heat transfer called conduction, convection, and radiation. So let's look at each one in a little bit of detail. And the first one is conduction. So conduction is the transfer of heat that requires direct contact between the two objects. So you see an example of a cow being branded. You have something that is very, very hot, and the heat is being transferred by direct contact because it's touching something. So it requires direct contact or collision between the molecules. If it's not touching, it can't be conduction. The next one is not a method of heat transfer. It goes along with conduction. It's called an insulator. What an insulator is it's something that prevents the transfer of heat by conduction. So what you see here is you see insulation in a house. Each one of these things is designed to prevent the transfer of heat by direct contact. Now, different insulators have different things, how they work, but the first one is they have high specific heat capacities. Okay, water is an excellent insulator because it's very, very hard to change the temperature of water. If you have a lake and you have it at minus 50 degrees Celsius right above the lake's not likely to freeze unless it's been that cold for a long, long time. Okay, because it's not going to work that way. Water is a very, very good insulator because it has a high specific heat capacity. The other way that insulators work is they work by not allowing the transfer of molecules. So like, for example, new windows are double and triple pane. And what they do is they have glass, and then in between the layers of glass, it's not actually glass, it's a plastic, but in between the layers, they have gases in here that are very, very low pressure gases. And what that means is there's very few molecules in here. Because there's very few molecules in here, it's very difficult for this to collide with the wall, obtain heat, and then collide against the other wall and transfer that heat. So the more panes that you have, the less likely it is for hot to be transferred inside to cold, or cold into hot, depending on what season it is. Next, we have convection. Convection says that higher temperature matter will rise because it has a lower density, and as it obtains a lower density, it rises, and as it has a greater density, it will fall as it cools off. So this circular pattern, this transfer of heat as things rise and fall, is called convection. Next, we have radiation. Radiation is the transfer of energy that does not require matter. So, for example, the sun heats the earth even though there's nothing in the way. So what that is that's the transfer of by radiation. Now we talked a little bit about radiation. We will talk a little bit about radiation in the next unit, but it will come up again when we talk about electromagnetic waves. So an example of this is infrared radiation. So why is it more dangerous to put your hand above a candle? What is more dangerous, putting your hand above a candle or putting it to the side? And it is, of course, putting it above. This is more dangerous. And the reason for that is if you were to go on the sides, everywhere there's going to be radiation. Radiation is relatively small. So that's infrared radiation, it's relatively small. There is going to be some conduction, okay, but air is a poor conductor. But the biggest reason why there's a difference between the two is convection. This right here, the warm stuff rises, and then the cool stuff is going to be to the side of the candle. So this warm falls, you're going to have some cooler air fall down to the side. So if you put your hand on the side, it's not going to be nearly as warm as if you put it directly above. What method of heat transfer does placing double-sided foil on the rafters of a roof present? And that is radiation. Okay, what this is doing is this is actually preventing what we call a radiant barrier that blocks radiant energy inside the home and outside the home. So during the summer, all the sun's rays that hit your roof, none of that heat, or not none of that, the heat that is transferred is vastly reduced because the heat comes in and is reflected off. During the winter months, when you have your heater on inside, the heat's going to come up to the attic and it's going to bounce off instead of being able to go through. And finally, it says determine 3 ways you can prevent the transfer of heat from outside to inside on a hot day. The first thing you can do is you just close all the doors and windows. Close off the house. What that does is that reduces the transfer by conduction. Okay, once you've reduced the transfer by conduction, the next thing you can do is you can actually block out the windows. You can either have insulated windows, or you can actually put foil on the windows and it'll work very well. It doesn't actually look very good, but if you put foil on the windows, it'll block it out as well. Okay, the last thing that you could do, there's actually a whole bunch of things that you could do, but you can actually install ceiling fans. You can put reflective coatings on the roof. You can add insulation to the attic. There's lots of things that you can do in order to prevent the loss of heat. But the number one thing is closing off the house. Okay, if you can close off the house by closing the doors, making sure all your windows are sealed, that's the most efficient way of preventing the loss of heat due to heat transfer.